Hey, this is Sesh. In this video, I'm going to show you how to delete items from a binary search tree or BST. This is the third video in a series on BST, the first of which covered BST structure and search, and the second covered insertion. You may want to watch these two preceding videos if you haven't already done so before getting into this one. And if you have, let's go right ahead. I'll start with a couple of examples to outline the process of deletion. Here's a sample BST I've been using for illustration. Which nodes do you think would be the easiest to delete from this tree? If you guessed 11, 19, 45, and 83, you're right on the mark. These are the leaf nodes, the ones that don't have any children. To delete any of them, all you have to do is to nullify the parent's pointer to it. This cuts the leaf nodes off the tree with no way to get to them again, so they will be garbage collected and returned to the memory pool. Okay, back to the original tree. Now, which nodes do you think would be the next easiest to delete? And if you guess 17, 38, and 69, you would be right again. If leaf nodes with no children are easiest to delete, then nodes with a single child, such as these, would be the next easiest. To delete a single child node, you simply redirect the parent's pointer from itself to its child, thus bypassing the node. The node is cut loose from the tree and cannot be reached and will be garbage collected. The most challenging deletion is of nodes that have both children. So, for instance, if we delete the root node 26 from the original tree, it would leave two subtrees hanging and the root pointing to nothing. What exactly do we do with all this so we get back a single BST? Well, you could start with an empty BST and insert all of these items one at a time. It would work, of course, but it seems like a waste, completely tearing down the original tree to build another from scratch just to delete one node. Instead, perhaps you could try to reorganize the structure you're left with after removing the single node. Now, we know that all items in the left subtree are less than all items in the right. Can we use this fact somehow to combine these subtrees into one BST? You may want to pause here if you want to think about this a little and come up with ideas. So one thought that comes to mind is if we could find the smallest item in the second subtree, we could then hang the entire first subtree off of that as its left subtree. We can see that 38 is the smallest item in the right subtree. How do we find it in the tree? We start at the root of the right subtree and follow the left children pointers for smaller and smaller values until we can't go left anymore. So here we go from 62 to 38. Not being able to go left any further means the left pointer of this node is null, which gives us the empty space to attach the left subtree. Alternatively, we can find the largest item in the left subtree, 19 in this example, and hang the entire right subtree off its vacant right pointer field. Restructuring either way is definitely a better approach than reconstructing the entire tree from scratch. But as you can see, it might result in a very lopsided tree, which is a downside when it comes to searching. It will take a lot more time to descend a skinny path than branch off quickly in a bushier tree. As it turns out, there is a third approach that is even better. But let's return to it after we get some code going for deleting leaves and single children nodes. Here's the header for the delete method. Target is the item to be deleted. The return value is the root of the resulting BST. The first thing to do is search and locate the target in the tree. We have already written the code for this in the search method in the part 1 video, and in a somewhat different guise in the insert method in the part 2 video. We should reuse one of them. Question is, which is a better fit? Well, as we saw earlier, to delete a node we need a pointer to its parent, since the parent's left or right child pointer would need to be changed. This is like insertion, where we need a pointer to the last node we encounter so we can attach the new node to it. So then the insert code is the one to reuse, specifically the part in which the search is being done. Of course, since we are searching for the item to delete, we want to find a match. And when we find the match, we want to continue with the process of deletion. So first off, we don't want to throw an exception. Second, Since the actual deletion process depends on how many kids the matching node has, and the code for this might get unwieldy, it's best to implement it outside the loop structure. So breaking out of the loop on a match would be a good idea. There is still an exceptional situation, which happens when the target is not found. You can't be asked to delete something that's not in the tree, so if no match is found, we will throw an exception. We'll only discover failure when PTR goes to null and we are outside the loop, so let's go ahead and write in our code there. Again, we use the illegal argument exception to indicate that the target argument was not legit. Now, if PTR is not null, it means we broke out of the loop with a match, and PTR is pointing to the item node to be deleted. So we're good to go. I want to first make a couple of changes to the variable names. I'll rename PTR to X, as an X marks the spot where the deletion needs to happen. And I'd like to change pref to P for parent, because it is the parent of X in the tree. Okay, now that we have that really critical fix out of the way, we can get on with the rest. Since the simplest kind of node to delete is a leaf node, let's code that first. We can tell that a node is leaf if both the left and right pointers are null. Now, before going on, I'm going to collapse all of the code up until now for search and throw in the exception, so we have enough room to write in the rest. Okay, we need to figure out if node X is its parent P's left child, as with 11 in this example, or its right child, as with 19. We already have this logic written up in the insert code, so we can reuse that part here as well. Except we need to change pref to P and temp to null. After the leaf has been cut loose, we need to return the root of the resulting tree. In this example, no matter which of the leaves is deleted, the root of the tree is still 26 and can be returned as is. But what if the leaf was also the root? This would happen if there was only one node in the tree, in which case deleting this node would empty out the tree and root would become null. We can identify the scenario by checking P for null, since the root node does not have a parent. And this has to be done ahead of the check for left, since otherwise we would get a null pointer exception on P when we check its left or right for null. Okay, now that we are done with the leaf case, let's move on to the case when X has one child. This is identified as either X's right child is not null or left child is not null. Again, let's collapse the leaf handling logic to make room for the code to follow. We saw that deleting a node with one child changes the parent's pointer to bypass the deleted node. So with X to be deleted and P being its parent, there are 4 possible pointer resets, depending on whether X has a right or left child, and on whether X is P's left or right child. 2 of these possibilities are illustrated in the example. 17 and 38 each have a right child, but 17 is its parent's right child, while 38 is its parent's left child. The other single child node, 69, falls in the same pattern as 17. We can write the code for these 2 possibilities, grouping them under the condition that x.right is not null. And I'm sure you figured out by now that we can write symmetric code for the other 2 possibilities, grouped under the else part for when x.right is null, which means x.left is not null. To summarize, all 4 possibilities are illustrated in these examples. And of course, as with the leaf case, the parent could be null and the x node itself is the root, in which case, after deleting x, the root points to x's child, left or right. We can code the scenario in each of the if and else blocks. Since the new root needs to be returned, we just return the child of x that is promoted to the root. This is pretty much all the code for deleting x when x has one child. What I want to do next is some cosmetic makeover that will make the code shorter and I believe more elegant. I'm going to start by changing the way I group the if-else parts. Instead of grouping according to whether x.right is null or not null, I'll group according to whether x is P's right or left child. You'll see why I'm doing this very soon. So here's our regroup code, and examples corresponding to the logical breakdown. Of course, we need to throw in the check for P being null, and we'll need to do it before the if condition where x is compared to P.right since otherwise we will get a null pointer exception on P. Okay, so you're saying, what's the big deal? The code doesn't look any shorter. But that was just a setup. Now we swing into some real action. We can rewrite each of the inner ifs like this. The right-hand side of each is called the ternary operator because there are three expressions combined by the question mark and the colon. And you read it exactly like the expanded if structure. The first part preceding the question mark is the condition, which in this case checks if x.left is not null. The result of the entire expression is either the second part, x.left, if the condition is true, or the third part, x.right after the colon, if the condition is false. The result is then assigned to the left-hand side, p.right in the if block and p.left in the else block. This is exactly why we regroup by x equals p.right or p.left. And actually the entire thing is a one-liner. I've broken it into 2 lines for lack of space. We can simplify even more. Since the expression is the same in both the if and else parts, we can set it up before the if-else, assigning the result to a temp reference which we then use inside the if-else. Now you might get carried away and try to convert this if-else into a ternary operator. Sadly, it won't work because the left-hand sides of the assignments are different. So we're stuck with the boring if-else. However, we can reduce the if block inside the p equals null if to a ternary operator return like this, and add in the root return at the end. Okay, so now we have much shorter and cleaner code, and can move on with the other real business we have left, which is to deal with the case when x has 2 children. Earlier in this video, before we started to write code, we saw that the 2 subtrees left from deleting a 2 children node could be combined. We could either attach the left subtree to the node with the smallest value in the right subtree, or attach the right subtree to the node with the largest value in the left subtree. But in either case, the resulting tree might be considerably taller, thereby slowing down the search. Fortunately, there is a better option that doesn't reshape the tree in such a drastic manner. Suppose we want to delete 26 from this tree. What we can do is to find the largest value in the left subtree as before. This is called the in-order predecessor, meaning the value that immediately precedes 26 in a sorted sequence. That value here is 19. We can find the in-order predecessor by making a left turn at 26 to get to the left subtree, then going right until we can't go right anymore. Again, just like we did earlier, to find the largest value. Let's point to this node with y. What we do next is to copy y's value into x, overwriting 26 with 19. And then we delete the y node instead. Why does this work? Before we answer this question, let's write in the code for this part. Let me first collapse the code for the one-child case so we can focus on the 2 children case. We have x at the node to be deleted and p is its parent. To find its in-order predecessor, y, we make a left turn first. Now, because we will be eventually deleting y, we need to have a pointer to its parent. So as we descend the tree, we'll carry the pointer p along 1 step behind like before. And then we copy the y data into the x node. So how does deleting y instead of x actually get the correct result? There are a couple of reasons why. First, because we found the largest value in the left subtree and wrote it over the x value, everything that remains in the left subtree of x is still smaller than x. And as you can see, everything in the left subtree of the x node, which now has 19, is less than 19. The second reason, which is a little more nuanced, has to do with the fact that y is guaranteed to not have a right child. This is true by the very process of identifying it as the in-order predecessor of x. If it had a right child, we would have gone further down the right path in search of the in-order predecessor, and y wouldn't be it. So how does y not having a right child help? It helps because deleting y cannot end up in a 2 children scenario. Either y is a leaf, as in this example, or it can have a left child. And we already have the code to delete a leaf or a single child node. But that code marks X as the node to be deleted, so we'll go ahead and reset X to point to the Y node. And we already have P positioned at dependent of X, so all that remains to be done is to execute the code for X as leaf or X as a single child node. Since this code appears earlier, we would need to jump to it. Now you might think we could do a recursive call, but there are a couple of reasons why we shouldn't. For one, it's not a repetitive process. After the leaf or single child node executes, we're done. And for another, the method includes a search which we don't want to repeat. There is a way to directly jump to any statement in a method, but it's generally considered to be bad programming practice, so we won't go there. A simple solution that does the job is to simply rearrange the code so that the check for two children is done first, followed by the leaf and single child cases, so that the two children case converts and falls through to the leaf or one child case. Nice and easy, no crazy jumping around needed. Okay, we're nearly done. One last round of simplification and that'll be it. First, the search and exception code. We don't actually need left, as we'll see shortly, so we rewrite the code like this, which also changes the if-else to a single assignment with a ternary operator. Second, the leaf and one child cases. I'm going to show you that the one child case does everything the leaf case does, and more, so we don't even need the leaf code. Start with removing the conditions, since we will have one code block that will serve both. The p equals null if block in the one child case is logically equivalent to that in the leaf case. This is because when you execute the former, if X is a leaf, then both x.left and x.right are null, and null will be returned as required. Also, the assignment of p.left or p.right in the one child case is logically equivalent to that in the leaf case, since if X is a leaf, then temp will be null. So we can just use a single block to serve both the leaf and one child cases. And here's the whole thing. To finish up, I want to run through a couple of examples of deleting a node with two kids to reinforce the algorithm. Say we want to delete 27 from this BSD. We locate the node at X, P is its parent. Then we find the in-order predecessor of X, which is a node at Y containing 26. And P moves over to its parent, 25. Next, the 26 at Y is copied into X, and X is moved to Y. This is the node to be physically removed. It is a leaf node, easily removed, resulting in this tree. In this next example, we once again want to delete 27. We locate it, then find the in-order predecessor and copy its value into X. Moving X over to the node to be deleted, we find it's a node with one child, and bypass it so that P's right points to X's left. And this is the resulting tree. Alright, that's about it for deletion. I hope you learned a lot from this tutorial. See you later.